doing this. I don't know if you've checked into our group before, but we have a little rule that once you check in, you've got to come back. So we.
In this video, we're going to introduce standing wave ratio, or SWR, and explain what it means in a simple, practical way. When your radio sends energy down the coax cable toward the antenna, that energy is supposed to leave the antenna and become a radio signal traveling through the air. If everything is matched well, most of that energy goes out as intended. If not, some of the energy is pushed back toward the radio instead of being radiated. SWR is the measurement that shows us how well that energy transfer is happening. You don't need advanced math or engineering to understand SWR. Just think of it as a basic indicator of how comfortably your radio and antenna are working together, and a helpful tool for building an efficient and reliable station. Before we get into SWR, let's talk about radio waves. A radio wave can be thought of as a moving pattern of energy that flows outward from an antenna in smooth, repeating cycles. As it travels, the wave expands through space at the speed of light, carrying the information that was placed onto it by the transmitter. The shape and strength of that waveform are influenced by many factors. A properly tuned antenna, good grounding and bonding, quality coaxial cable, and correct polarization all help the wave launch cleanly and efficiently. A radio wave has several basic features that help us understand how signals travel and why SWR matters. Every radio wave has a frequency, which determines what band we are operating on, and a related wavelength, which is why antennas are built to specific lengths. The amplitude of the wave represents its strength, while the wave itself travels outward at the speed of light. Radio waves also have polarization, such as vertical or horizontal, and they carry information through modulation, like AM, FM, or digital modes. When your antenna is properly matched to these characteristics, energy transfers efficiently and most of the radio wave is launched into space. Let me break it down for you. Oscillation is the repeated back and forth change of a value over time, such as voltage or current rising above and falling below a reference point. In radio systems, oscillation is what creates radio frequency energy. Electrical signals continuously move in a smooth, repeating pattern that forms a wave. This steady oscillation is what allows energy to be transmitted as a radio signal instead of a one-time pulse. Amplitude describes the size or strength of that oscillation. It represents how far the wave moves above and below its center or resting point. In practical terms, higher amplitude means more signal strength or power, while lower amplitude means a weaker signal. Together, oscillation and amplitude describe both the motion and the strength of a radio wave, forming the foundation of how signals are generated, transmitted, and received in amateur radio. Polarization describes the orientation of a radio wave's electric field as it travels through space, and it plays a major role in how efficiently amateur radio stations can communicate. When an antenna transmits, it launches energy with the electric field aligned in a specific direction, most commonly vertical or horizontal, and receiving antennas respond best when they are oriented the same way. For example, a vertically mounted antenna produces a vertically polarized wave, while a horizontal dipole produces a horizontally polarized wave. If the transmitting and receiving antennas are mismatched in polarization, a significant portion of the signal can be lost before it ever reaches the receiver. In practical amateur radio operation, matching polarization between stations improves signal strength, clarity, and reliability, making it an important consideration when choosing antenna types and how they are installed. Modulation is the process of impressing information onto a radio wave so that it can carry voice, data, or other signals from one station to another. In amateur radio, the transmitter takes a steady radio frequency carrier wave and intentionally varies one of its characteristics, such as amplitude, frequency, or phase, in step with the audio or data being sent. These controlled variations encode the information onto the carrier, allowing it to travel long distances through space. At the receiving end, the radio reverses this process by detecting and decoding those variations to recover the original sound or data. In simple terms, modulation is what turns a plain radio wave into a meaningful communication signal. Polarization between stations improves signal strength, clarity, and reliability, making it an important consideration when choosing antenna types and how they are installed. On a standing wave pattern, such as the RF wave on a mismatched feed line, the high-voltage spikes occur at the voltage antinodes, the peaks of the wave where the electric field is strongest. These points form where the forward and reflected waves add together, creating maximum RF voltage and minimum RF current. They often appear near open ends, antenna feed points, or impedance mismatches. The low-voltage points occur at the voltage nodes, the dips or zero crossings of the standing wave. In amateur radio, an SWR of 1.0 to 1 would be perfect, but in the real world, anything 1.5 to 1 or lower is excellent, and up to about 2.0 to 1 is generally acceptable for normal operation. These values mean that most of your transmitter's power is being delivered to the antenna and radiated as a signal, rather than being reflected back toward the radio. As SWR climbs higher than 2.0 to 1, more power is reflected, efficiency drops, and the chances of problems increase. Very high SWR can cause radios to reduce output power automatically, overheat components, or in extreme cases, stress or damage the transmitter's final amplifier. We measure SWR using an SWR meter when constructing and installing an antenna. Also on high frequency, we use an antenna tuner placed in the feed line between the radio and antenna, or with the built-in SWR meter found in many modern radios. These tools compare forward power and reflected power and display the ratio. This gives us a quick and easy way to check that our antenna system is operating in a safe, efficient range, so our signal gets out cleanly and our equipment stays protected. SWR issues in the shack can be reduced by ensuring the antenna system is properly matched and providing a controlled path for RF energy. This starts with using an antenna that is correctly sized for the operating frequency and installing it with a proper ground or counterpoise when required. Adding a choke at the antenna feed point helps prevent RF from returning on the feed line, while good station bonding and grounding keep RF from flowing on equipment and cables. When needed, an antenna tuner can be used to improve the match seen by the radio, reducing reflected power and keeping RF where it belongs, on the antenna instead of inside the shack. Managing SWR starts with measuring it correctly and making sure the reading is meaningful by checking frequency, power level, and meter settings. Once high SWR is confirmed, the next step is to inspect the feed line and connections, since loose connectors, damaged coax, or water intrusion are common causes. If the feed line checks out, attention turns to the antenna itself, adjusting its length or geometry in small steps to bring it closer to resonance on the desired frequency. If you aren't getting the results you expected, try adding a choke or a counterpoise, and always recheck your results with a meter. A counterpoise is an essential part of an antenna system because it provides the return path that radio frequency energy needs to flow properly. When an antenna transmits, RF current must leave the radiating element and return through something else to complete the circuit, and the counterpoise fills that role. It may take the form of radials, wires, metal structures, or other conductive surfaces, and it does not have to be connected to earth ground to work electrically. Together, the antenna element and the counterpoise act as a complete RF system, sharing equal and opposite currents. When a counterpoise is missing or poorly formed, RF will search for unintended return paths such as coax shields or station equipment, leading to high or unstable SWR, unwanted RF in the shack, and unpredictable antenna performance. A well-designed counterpoise improves efficiency, stabilizes SWR, reduces interference, and allows the antenna to behave as intended. Adding a choke at the antenna feed point helps prevent RF from returning on the feed line by blocking unwanted RF currents that try to travel along the outside of the coax. Adding a choke at the antenna feed point helps prevent RF from returning on the feed line by blocking unwanted RF currents that try to travel along the outside of the coax. A choke, often made by winding coax into a coil or using ferrite beads or cores, acts as a high-impedance barrier to these unwanted currents while allowing the desired signal inside the coax to pass normally. By stopping RF from flowing back toward the shack on the feed line, the choke keeps the feed line from becoming part of the antenna, reduces RF in the shack, stabilizes SWR, and helps the antenna system radiate more efficiently. A ferrite bead is a small but powerful tool used to control unwanted radio frequency energy. Made from a magnetic ceramic material called ferrite, it is placed around a wire or cable to suppress high-frequency noise while leaving the desired signal largely unaffected. At normal operating frequencies, such as DC, audio, or the intended RF signal, the ferrite bead has very little effect. However, when unwanted high-frequency noise or stray RF currents appear on the line, the ferrite bead presents a high impedance and absorbs that energy, converting it into a tiny amount of heat. In this way, the ferrite bead acts like an RF sponge, soaking up noise that would otherwise travel along the cable, interfere with equipment, or cause unwanted radiation. In radio systems, ferrite beads help reduce common mode currents, minimize interference, and improve overall station stability without changing the signal you actually want to transmit or receive. In wrapping this up, understanding SWR isn't about chasing a perfect number. It's about understanding what your station is telling you. When you know how radio waves form, how energy moves, and how your antenna system accepts or rejects that energy, SWR becomes a simple diagnostic tool instead of a mystery. By paying attention to your antenna, feed line, grounding, counterpoise, and chokes, you're not just lowering a meter reading, you're building a station that is efficient, stable, and predictable. Because when your antenna system is working properly, your signal gets out cleanly, your equipment stays protected, and amateur radio becomes more enjoyable and more reliable.